Welcome back, architects and developers. Today we are tackling the core building blocks of reliable AI applications, building independent logic units within LangGraph. We will shift from tangled scripts to robust, modular agent design. Let's get started. Let us kick things off by defining our fundamental building block, the node. When building agentic workflows, especially in frameworks like LangGraph, a node is simply a Python function. But structurally, it acts as an independent logic unit. It takes the current global state of your application as its input, does its specific job, and outputs a state update. The major paradigm shift here is moving away from monolithic, tangled code where every function knows about every other function. By forcing our logic into these isolated units, we ensure that each node focuses on exactly one task, whether that is querying an LLM, validating a document, or calling an API. The node doesn't care what happened before it or what happens after it. It only cares about the state it receives. This isolation is the absolute foundation of building enterprise-grade, scalable AI. Take a look at this flowchart to visualize the isolation. On the left, the global state flows into the node function. Inside that green box, our independent unit performs its compute or LLM logic. Crucially, the node does not mutate the global state directly. Instead, it outputs a discrete state update dictionary. The framework then catches this dictionary and safely merges it back into the master state. This guarantees our logic unit remains completely decoupled and safe. Why should we obsess over building independent nodes? Because monolithic AI applications are a nightmare to maintain. If you put your prompt generation, LLM invocation, and API execution into one massive script, a single failure crashes the entire system, and debugging becomes impossible. By treating nodes as independent logic units, we enforce the single responsibility principle. Your fetch data node only fetches data. Your summarize node only summarizes. This modularity yields incredible benefits. First, testability. You can unit test an independent node perfectly by just handing it a fake state dictionary and asserting its output. There is no need to run the entire multi-agent graph. Second, reusability. If you build a robust, independent node that queries a SQL database, you can drop that exact same node into 5 different agent applications without changing a single line of code. This diagram contrasts the two architectural approaches. On the top left, the monolith is a red box of tangled logic and state a single point of failure. On the right, we see the modular nodes approach. The workflow is cleanly divided into fetch, validate, and execute. Because each blue box is an independent logic unit, if the validate node fails, it fails in isolation, allowing us to catch the error, log it, and trigger a safe fallback mechanism. How do we actually construct one of these units? Structurally, a node is just a standard Python function, which can be either synchronous or asynchronous. Its signature is beautifully simple. It takes a state object, typically typed as a typedict or pydantic base model. When LangGraph calls your node, it passes in an immutable copy of the state. This is a critical security feature. It prevents your function from accidentally modifying data that belongs to another part of the system. Additionally, your node can accept a second optional config parameter, giving you access to session IDs, user IDs, or specific LLM configurations. After your logic runs, the node must return a Python dictionary. It does not return the whole state, it only returns the specific keys and values it wants to update. This keeps the data payload lightweight and the node's intent crystal clear. Let's trace the execution in this sequence diagram. The graph state engine initiates the process by passing an immutable state copy to our independent node function. The node activates, safely executing its internal Python or LLM logic without touching the outside world. Once complete, it sends a simple update dictionary back to the engine. The engine takes over again, applying reducer functions to safely merge those updates into the master state. Let's deep dive into how state isolation truly works. In amateur software design, functions manipulate global variables directly, leading to catastrophic race conditions. In our architecture, nodes never write directly to global memory. They simply propose updates. The magic that makes this work is the reducer pattern. When your node returns its dictionary, LangGraph intercepts it and passes it to a reducer function defined in your state schema. If your node returns a string, the default reducer simply overwrites the old string. But if your node returns a new chat message, a reducer like add messages safely appends it to the existing conversation history. This isolation is the secret to parallel execution. Because nodes are perfectly independent and only output dictionaries, you can fan out and run 5 different nodes simultaneously. The framework will gather all 5 dictionaries and safely reduce them into the master state without a single data collision. Observe the parallel execution safety in this diagram. The master state feeds data into Node A and Node B simultaneously. Node A searches the web, while Node B runs calculations. They both finish and spit out their respective dictionaries. These dictionaries hit the yellow state reducer node. The reducer methodically merges the data, guaranteeing that the master state is updated flawlessly, regardless of which node finished first. Let us look at the actual Python code to build one of these units. Step 1 is defining your state schema using type dict, explicitly stating what data exists, like document content. Step 2 is writing the Python function itself, def fetch document, state, agent state, comma. Step 3 is crucial for senior engineers. Handle your errors internally. You should wrap your API calls in try/except blocks inside the node. If the document fetch fails, your node shouldn't crash the program. It should catch the error and return an error flag in its output dictionary. Step 4 is returning that discrete update, for example, returning a dict with just the document content key. Finally, step 5 is registering this independent unit with your application by calling builder.addNode. You pass it a string name and the function reference. You have now securely plugged an independent logic unit into your enterprise architecture. This class diagram maps our code structure. At the top, the type dict state defines our data contract. Our node, fetch document, reads this contract during its execute method. Below, the state graph orchestrator is responsible for calling the addNode method, officially registering our logic unit into the wider agentic workflow while keeping the node's internal logic strictly encapsulated. Let's apply this to a high-stakes real-time use case, an enterprise loan processing pipeline. We need to fetch an application, validate the data, run a credit check, and assess financial risk. If we build this monolithically, the code becomes an unmaintainable nightmare of nested if statements. By building independent logic units, we create distinct nodes for each task. The brilliance here is the isolation. The check credit node doesn't know anything about PDFs or document parsing. It simply expects a customer ID in the state, calls the credit bureau, and returns an integer score. This independence allows for fail-fast routing. If the validate document node detects missing income data, it returns an error flag. Our graph's conditional edge sees this flag and instantly routes to a rejection node. We gracefully halt the process without ever firing the expensive credit check API. This is how you build efficient, cost-effective enterprise AI. Here is the state diagram for our loan pipeline. The flow moves from fetch to validate. At validate, the independence of the node shines. It evaluates the data and outputs a status. The graph reads the status. If the data is valid, execution flows normally to the credit check node. But if an error flag is raised, execution instantly branches down to the compile rejection node, bypassing unnecessary compute and API costs completely. As we conclude, I want to leave you with an advanced architectural concept. We said a node is an independent logic unit. But that unit doesn't have to be a simple Python function. In LangGraph, an entire compiled graph with its own complex internal routing and state can be registered as a single independent node within a larger parent graph. This is called a subgraph. It allows you to build massive multi-agent teams where a supervisor node delegates work to specialist team nodes, completely abstracting away the internal complexity of those teams. Mastering node independence is the absolute key to scaling from experimental chatbots to reliable, enterprise-grade AI systems. Thank you for joining this masterclass. I invite all learners to like this video, subscribe to the channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Keep building. Our final diagram visualizes the power of subgraphs. The parent orchestrator graph on the left calls the specialist node. But notice the dashed lines inside the specialist node. It is actually an entirely separate graph containing internal node 1 and internal node 2. The parent graph has no idea this complexity exists. It just passes the state in and safely receives the updated state back, proving the ultimate power of independent logic units.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. We have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see this is are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper, it would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.